SwayamPrabha. Digital India. Educated India.
In your lectures, you have seen how we developed a relationship between your voltages and deflection of control surface. Now we will verify experimentally whether the data we are getting is a linear sort or non-linear sort. As I have already told you in my lectures, this is a digital inclinometer and currently is showing minus 20.07 degree. How to check whether this is negative or positive? You can see a small symbol here indicating a negative slope, which I have already mentioned in my lectures. Now, while deflecting this control surface, as you can see, the angle is changing, whereas slope remains the same. That means this is a negative slope. Now, while I will be deflecting it in opposite direction, you can see slope is still negative, but the angle value has changed. Now, further deflecting it in opposite direction, you can see at this particular deflection, your slope angle has changed, and now the angle which it's showing is 1.93. Now, while in my lectures I have already explained how to determine your reference point. Now, this wing is at some angle with respect to your ground. That's why if you want to take a reference value, say if this is your neutral position or your control surface deflection is 0 here, you are getting a default angle of minus 12.09 degree. Same you can verify with your inclinometer, that is analog inclinometer, it's showing somewhere close to 12 degrees. Now, while performing experiment, your deflection will be controlled through your control stick in aircraft, and these angles will be determined in both positive and negative direction. So, first let us set a reference point. Okay. Now, as I told you in my lectures, that with this deflection surface, with deflection of this surface, you will be getting a respective voltage with that deflection. Now, how this voltage was calculated, we showed that during the setup of experiment we required an inclinometer, a potentiometer, a laptop interfacing software, and a data acquisition system, that is NIDAC we are using. Now, this is a small potentiometer, not used in this particular application, but as I told, it had a 3 terminal. These are the 3 terminals. This is a rotating contact switch. On varying this, you can vary the voltage between these particular 2 pins. And while then same principle you can apply to control while calculating your voltage for deflection of this control surface. As you will deflect this control surface, it will act as a rotating switch, and corresponding to that rotating switch, a voltage will be shown in your LabVIEW software on that particular angle, and then particular value of voltage you can calibrate or map that on your linear scale. So, we will be showing you how that experiment is performed. Now, I mentioned you how to use this potentiometer to determine what will be the deflection of your control surface. The phenomena was same, but for this aircraft, this is your potentiometer. As you can see, a string attached to your control surface. Now, as my colleague is deflecting control surface, this string, the tension in this string varies, and according to this, your potential or voltage corresponding to a particular deflection in control surface is seen in LabVIEW. It works on the same principle, but instead of this manual rotation of this contact switch, here a string is attached that is varying the resistor, and according to that your voltages for different control surface, different deflection for this control surface, the voltage different varies according to deflection. Now, we will be seeing how to perform the experiments. Now, in performing this experiment, while drawing that block diagram, we showed that we need an interfacing software to determine at what particular deflection what will be the voltage of that deflection. Now you can see as this is a LabVIEW program which we use for determining voltage against deflection of control surface. The interface consists of an output screen, a channel which determines which particular control surface or parameter you want to select. Now we already told you in this we determined 16 different parameters for this aircraft, for which the channel for aileron deflection we are doing experiment to determine what is the relationship between voltage and deflection of ailerons will be on channel 13. So my colleague has selected channel 13 as to display what will be the output corresponding to that, and as you can see that voltage part, as I will be deflecting this control surface, you can see the voltage is varying according to deflection. Now we have to map this voltage as per deflection of my control surface. Now first point while performing this experiment was to determine my reference point, that is when my elevator or my aileron is with 0 deflection. Now while setting reference, that is when my deflection of aileron is 0, my angle which inclinometer is showing is minus 12.12, and corresponding to that the voltage which I am getting is 2.4 volts. Now my colleague will set this as 0 angle. That means this is when aileron deflection is 0. Now my colleague will deflect this control surface both in positive direction and negative direction with respect to your reference point. Now this was my reference point. My colleague will be deflecting this control surface in both direction with a regular interval. So first deflecting it in downward direction. See, as this control surface is deflected in downward direction with respect to reference point, your angle is changing. Now deflecting it in opposite direction, angle was changing, and corresponding to that you will be getting different voltages. So while varying your control stick, you can determine what voltage you have to give to your control stick, or what with particular deflection what voltage you are getting in your LabVIEW you can determine using our LabVIEW software. Now after setting my reference point, the next step was to load your LabVIEW program and deflect your control surface in both direction, downwards and upwards with respect to your reference point. So earlier I told you my reference point was minus 12.05 degrees or somewhere close to that. Now while performing experiment, as you know, first step was to determine your reference point, and that is when the deflection of control surface was 0. For that, for our aircraft, that 0 deflection point is minus 12 degrees, and corresponding to that my colleague will set angle as 0. The voltage which I am getting, that will be recorded in your LabVIEW. Then further to continue performing to calibrate your control surface, you have to deflect your control surface in either direction with reference to your initial point, that is minus 12 degree. You have to move it in either direction. So I am deflecting it by 1 degree in negative direction, that is minus 13 degree, and corresponding to that the voltage my colleague will record in LabVIEW code, that will be recorded as minus 1 degree. Further I will shift it downwards to minus 2 degree, that is minus 14, and that will be recorded in LabVIEW as minus 2 degree, and corresponding will be voltage will be recorded in your LabVIEW code. Now further shifting it to minus 3 degree, that is minus 15, and corresponding voltage will be recorded in your LabVIEW. Now similarly you have to take 10 to 15 readings in particular direction, so you get a good accuracy of voltage versus your control deflection of control surface. Now I am shifting it in positive direction. As you know, my reference point or initial point was set at minus 12 degree, that is 0 deflection of control surface. Now, in upward direction with 1 degree, that is minus 11 degree, the corresponding voltages will be saved in LabVIEW code as voltage corresponding to 1 degree deflection. Further, now shifting it to 2 degrees, that is minus 10 degree, and corresponding voltage will be recorded as 2 degree. Further shifting it upwards to 3 degree, that is minus 9 volt minus 9 degrees in our inclinometer, and then corresponding voltage will be saved as 3 degree in our LabVIEW code. Similarly, you have to take 10 to 15 readings in either directions to get a good result for your calibration of performing this experiment. We will be seeing how the data were accumulated, and we will be plotting a relationship between your control surface deflection and voltages. Every time we perform this experiment, a data file will be saved in your laptop or PC, whatever you are using, that is inbuilt in our LabVIEW program. After that data is recorded, you can analyze what is the relationship between your control surface deflection versus voltage, which, as I told you during flight data recorder, for digital circuits you require the output will be in terms of voltage or current. So, there you require this voltage reading, so that you can determine what was my deflection of control surface. So, we will be showing you the data which we recorded while performing this experiment. The experiment is lengthy, since it requires 15 to 20 readings in either directions. We will be showing you what the readings we got, and we will be plotting and what was the value of m and what were the value of c, that is intercept and slope, and how using that you can determine what were the control surface deflection if particular voltage was given to it.
Welcome back, friends. While performing experiment for calibration of control surface, we told you that you have to first set a reference point, and then after that you have to deflect your control surface in either directions and take as much as readings, say 10 to 15 readings in either direction, so that you get a exact relationship between control surface deflection and respective voltages. So we performed the experiments, and these were the readings for different control surface. Now for elevator, these were the readings obtained while we deflected your control surface in either direction. We took 10 readings in different directions. Now, in order to establish the relationship between the control surface deflection and your voltages, we have to find relationship between these, and what will the value of slope and intercept. Easy way to do this is you can take this data direct to Excel file, and using a curve fitting tool you can directly access what is the value of slope and intercept. So let's find what is the intercept and slope for this voltage and angle deflection we obtain for elevator calibration. Let me access Excel. I'll paste this value in Excel. Now, in order to plot a graph between these two data points, all you have to do is go to insert and select scatter plot. I'll select data since and add. Now since this is for elevator calibration, I'll give series name as elevator. Now your X data will be angle, and your Y data will be corresponding voltages. then OK. Now as you can see, this is a straight line, but you can see here the line is a little bit of smudge. This is because this data is not arranged in a ascending or descending order. All you have to do is select these two data and click sort and filter and arrange either from smallest to largest or largest to smallest. Okay, now you can see this is a straight line. Now to get a what is the value of slope and intercept, we have to go to design, add chart element and trend line. Click on more trend line options. Since this we have selected a curve fitting of linear sort, so this will be linear, and to see what is the equation of that line, you have to click display equation on chart. So this is equation of a line which you want for a elevator deflection with respect to voltage. Now this we have derived from Excel. Now what if we don't have this Excel, or we want to do it manually? Let's see what is the slope which we get, assuming this the data point we get will lie on a straight line. So as you know, slope is y2 minus y1 upon x2 minus x1. So let's calculate what is the slope you're getting using this formula. This is your, suppose, y2 minus y1. This is your y1 divided by x2. This is your x2 minus x1, and enter. This is the slope we are getting, and which is very close to we are getting using curve fitting. Now as you know, intercept will be the point at which your angle will be 0. So you can see from this data readings it's 2.58. So these are the values which we got for slope and intercept using analytical method, not using the line or curve fitting. Now in a similar fashion, you can do for different control surfaces. While performing experiment, we took data for aileron deflection, and these were the readings we obtained. Let's find out what are the value of slope and intercept. Same way, we'll copy this data into Excel file, paste, and again let's first use sorting and filter to arrange this data in ascending or descending order. Now again go to insert, add scatter plot, click on scatter plot and select data, add, this is for aileron, so we'll add series name as aileron. Now your X data will be deflections and your Y data will be corresponding voltages. Click OK and OK. And here as you can see, this is a straight line which we got for voltage versus angle deflected for aileron. Now same way, in order to get equation of straight line, go to add chart element, trend line, more trend line options, and select display equation on chart. So this is the slope and this is your intercept. And same way we can verify using analytical method. Since you can see for 0 reading is 2.35, so this will be your intercept, and the slope will be y2 minus y1, y2 minus y1 divided by x2 minus x1, 0.103, and here we are getting 0.144. So it's quite accurate even if we take using analytical method. So this was all regarding to how to calibrate your control surface. In coming lectures, we'll see how to analyze data we collect from FDR.